You want to? Just sit this way, starting second row. Okay. Let's fill in from the front. Any further back? Please don't go any further back than row 3. Yes. Well, testing, 1, 2. Can you turn me on? Testing, 1, 2. It's mic number 1. Testing, 1, 2. Maybe it's going back. Check, 1, 2. Check, number 1. Oh, number 2. All right.
I hope they charge it back to you since yesterday.
Testing 1. Oh, there we are. Welcome, everybody. All right. It's interesting that we would be here at a session on sonification and have sound problems. So I'm Jim Adams. I'm part of the advisory committee here at Scifest. And also I work at NASA, which is important only because Wanda and I, today's speaker, have crossed paths many times during our career, but only ever really met until I first came to Scifest last year. So Wanda started by getting her Master of Science, Physics, from the University of Puerto Rico in San Juan. And over the course of her career, she's had several internships at NASA's Goddard Space Flight Center, where I was at for 17 years. And then she's also obtained a doctorate in astrophysics from the University of Glasgow. And along the way, she became blind. And so she had to adapt, and she's here to tell you about that story, but she's developed some amazing software that takes data found by the probes in space, one-dimensional and two-dimensional data, and turns it into sound so that she can actually analyze the data along with her scientific peers. So it's actually a wonderful honor to have Wanda Merced with us here today, and please give her a warm welcome.
I applaud myself. I did 9 internships at NASA, and I wonder why I never saw Jim on the hallways. So thank you for the wonderful introduction, and thank you so much for supporting, right? It's really hard when you have such wonderful people walking around to come to this room to listen to this humble presentation. So as Jim said, I've been working on using sound to analyze astronomical data for I began doing this in 2005. When I began, I was losing my sight, and it's a project that began as an effort to bring people that were losing their sight to get an idea of what these numbers may look like. But when I got to work with this prototype, I said, no, I'm not going to get just an idea, I'm going to get much more from this, because I want to do science at the same level as my peers. Why using sound to analyze data or to see better? Are you seeing the presentation on the slide? I may need your feedback because sometimes I do not pass the slides. Is that the presentation?
No, Wanda, it's not. Do you need me to pull it up?
Yes.
All right.
You said let's have it in.
Actually, what we've got is MP3s. She knows how to use a Mac better than I do. Awesome.
So. That was supposed to play later. It's not a surprise anymore. How do you do that? Where are we? The Finder. Press the stop button there somewhere. You should see the stop button.
Hit the space bar. There we go.
No, it's playing. Sorry. Blind people, we talk a lot and we make a lot of mistakes. We step on people and we don't care. Look at that. I'm starting to care now. It's still playing.
Yeah, I see the stop now. I want me to.
Yes.
All right. Oops. I'm trying to do this upside down.
So you play command tab.
Push stop.
No. What icon are you seeing on the screen?
I'm seeing 4. A coffee cup, iTunes, which is highlighted.
I think yes.
Wow. There you go.
The PowerPoint presentation.
Is next to the right. There you go.
Okay.
I'm a computer scientist. What's wrong with me? So why sound to see better? When I was doing my master's and my bachelor's in physics at the University of Puerto Rico, what I was doing was radio astronomy. And I wanted to keep doing radio astronomy, but I needed to find a way to continue doing my science. And we began this project, as I said, as a notion to bring people with sight impairments or visually impaired to get an idea of the numbers plotted on the screen. But I wanted really to get much more than that. I wanted to do my science. So I began exploring this possibility with my very good mentor, who was I'm not associated with NASA at all, even though I've been there 9 times. I'm not associated with them. I'm working at the Center for Astrophysics as a postdoc, and it's a Harvard-Smithsonian Trust. My mentor there, he took me, and we began working on this prototype. The basic idea is this: the information the telescopes gather, the satellites orbiting Earth, those are measurements. It's light. We get those measurements. The measurements then are processed, and then The astrophysicists take those measurements and they plot them on a screen. And they use colors and different lines in order to visualize whatever they want to visualize. They come to the data with a project at hand or a guess at hand, right? And so the idea is that when you use sound parameters in order to convey the information this data is portrayed, you're using a technique that is called sonification, which is to use sound as an algorithm visualization or use sound to convey information using mainly non-speech sound. It will be the auditory analog to data visualization. So we wanted to convert those charts that the astrophysicists regularly see on the screen. We wanted to convert them into sound, but we also wanted to be able to listen to those sound parameters and be able to get some extra information. So let me give you an example of some data sonified, so you know what sonification is. Is that okay? It's not a surprise anymore because you already heard it, but that's okay. I'm going to play, I need to turn
That's pretty loud.
iTunes has no windows. iTunes has no windows. Microsoft Shop for iTunes. iTunes has no windows. Dock, Launchpad, Sky, Contact, Command, Create, Type, iBook, My System, Keynote, Safari.
I know what he's saying.
iTunes, Windows, Album, Interactive Album, Present Action C, YNCA, Present App, Note, YNCA, Present, YNC, Present, Stop Interacting with Album.
I need to go to a file in here called Orion.
Present Action C test.
All right, so it's this presentation Scifest, Sir Africa teachers, there's WinCME and ACME.
Orion. Sorry for these problems, it shouldn't happen. Brightest stars. Do you see it there?
Yes.
Okay. Where is the file? Do you see it? No?
I see a soundtrack.
Kevin, can you bring the arrow to the iTunes and find the file called Brightest Stars? All right. Can you put the arrow on the file? It will play. So that is sonification. I have a student in Aberdeen who is working on developing a software that blind people can use in order to get a notion of the sky, the night sky. So he's trying to convey distances. He's trying to convey also something that we call average magnitudes. So in this case, in this file, those are the 5 brightest stars. That may be Vega, which are the other 4?
Sarah?
There's yes, there's yes. So the thing is that for blind people, the concept of distance is at the PowerPoint.
Yes.
Yes, the concept of distance is a choreography. Is that it?
Mm-hmm.
Okay. So you're seeing the names there. Vega, Alpha Centauri. So Cygnus, yes. So you hear them first. The first star, the second one, the pitches, the tones, the pulses will change according to the apparent magnitude and the distance from us. Because we have so much problem with distance, we don't get a sense on how distant things are from us. People talk about the sky, And we really don't have that concept in our heads as you do. And regularly when we're exploring the sky, we are looking down, touching Braille images. We are not looking up like you guys do. For us, the concept of distance is very difficult. So those are the 5 brightest stars. I don't know if at that volume you can notice the change of in the pulses, or you can identify the changes in distance and brightness. But now I'm going to show you the sonification of a constellation called Orion. You see Orion there?
It's 4 down.
Yes. Can you bring the arrow on Orion? Alright? I think I need to stop that first. And we were successful, that's good. Okay. So this is the other sonification that he made. What he's trying to do is to convey first the 4 main stars of Orion and then the 3 stars in the belt. One at a time. Variation in pitches will tell you the apparent magnitude, and the variation in pulses will tell you how the distance from us is varying per star. So first you will hear the 4 stars, and then the stars in the belt of Orion, and then you will hear them all. And you're not hearing them all, it be gone. That's good. Is the sound good? Can you feel the changes?
Yes.
Are you sure? Okay. So other kinds of sonification. This is specifically, it shows these parameters to convey this information to us, even to you. But sometimes we use sound parameters in order to increase our sensitivity to the detection of events in data that is visually noisy. Do you know what is visually noisy data? It's too much data. Many peaks. Sometimes it's effects of the systematic effects on the data. But sometimes, embedded in that noise, you can find the things that are of importance. See? It has happened to us. We have found things in the data that has been of importance and that are embedded just in the noise. That otherwise, if we wouldn't have heard the data first, and we would have applied data reductions, and we would have applied smoothings of the data or other expansions or other agents, we would have lost those signals in the data, regardless the degrees of freedom that you would have given to the data. Are you with me? That's good. Okay, so I'm going to show you. This is a CME that I'm in love with, because I was working with at the University of Puerto Rico, and it was the first data that I used to analyze intensities of magnetic fluctuation intensity. Yes, it's my first data. It's the first data that I used to load into the Xonify, which is a program that I'll show you later, and that allowed me to listen for changes in. Okay. So I'm going to stop this one because you may be tired of it. And do you see a file called ACME?
Right. 2 more. 1 more.
Okay, and the arrow. There we go. Okay, so this is what you will listen. It was a massive burst, and it's a coronal mass ejection, but it was a massive burst of ionized gas or electrically charged gas that happened on the 24th. They began happening. It was 3 bursts that happened between the 24th of October 2003 and the 31st of October of 2003. There were 3 bursts, the massive. I just took the first one and the last one because those were the ones that I had access to. And you will not hear so many 6 days or 7 days of data because you will have to sleep here. What I did is that I compressed the data You will hear the first burst arriving to the satellite, then a little bit of the noise floor, and then you will hear to the second burst. Are we?
Yes.
It's very fast played. So it's not the way that I use to analyze the data, but I'm going to play it. Can you
Raise the sound.
raise the sound? Thank you. Now that's a very fast. This is the data very fast, right? Arriving to the first one, arriving to the eighth satellite or spacecraft. When you hear it like this, it doesn't have any meaning. You just know that something is increasing and something is decreasing, and if you know that is magnetic fluctuation data or any component of that data, then you know that something is happening. But it's really hard for the ear at this stage to get a sense of how one data point is changing in relation to the next one. In order to do that, you will have to change the tempos, you will have to sit down for a long time and listen to the data. And I think that maybe, I'm sorry, I'm not allowing you to listen, right? You came to do that. Okay, so that's ACE. I'm going to stop it. Is that yes, that is. So that is arriving to ACE. Now, please listen how the coronal mass ejection arriving to the wind satellite. And this is sonification, don't forget. Okay, did you see one called wind? Yes. Is that good? Okay. You're here. Completely different, right? Same tempo, same component. That's what you want to get. So each data set has its own voice. Same timbre, same pitch, equally pumped. So when I listened to this data, when I analyzed it the first time, I was trying to listen for changes in the spectral index, because that would give me an idea of things happening in the space within the planets, see, in the interstellar media. Shall I leave it longer or shall I stop it? I want to stop it highly. That's the first one, on the 24th of October. Okay. Can we stop it? Here in South Africa. Here in South Africa, we have
the SKA, which will gather, if I heard well, it will gather 10 times the amount of information the internet processes in one day. And this I heard it from Michael Masuda, who was the Minister of Science last year. And I was in the car with him, so I don't think I made a mistake. And he said that even if that is something like unconceivable to us. Those systems, in order to process the data, in order to get the most of the data, with uncertainty there is, we will need to support the scientists working with the data, allowing them to use their senses other than the visual sense in order to get the most of the data. So we said, perhaps using the sound, you can stop it.
He's trying.
Something else. Yes. No, you stopped it.
Copy.
Yes, but I just had to get close to the computer. So, do you see the PowerPoint presentation? That is good. And I guess we're beyond that. So, I've been analyzing data, and I've been working with this magnetic fluctuation data, and I've been gathering X-ray data, and I've been listening, crossing data from Venus to Mercury, from Mercury to Venus, back and forth, tons of data. But this is from Wanda's perspective. Wanda is listening, and remember, Wanda wants to find something. We need to, in order to do this seriously, we need to really prove, if we want to be able to get ready for this torrent of data, we need to be able to really prove, undoubtedly, that it will increase the sensitivity, not only of the blind people, but what about the sighted people? Because really, Wanda is one blind astrophysicist. The other 99.9999999 and then infinite % of the astrophysicists, they're sighted. So I need to bring something that not only will support me, but that will support them in the data analysis, if I want this to move forward. Are you with me? If you don't agree, please let me know, because my reasoning may not be that a state of the art. So just let me stop this for once. Do you see the icons?
There.
They stopped. All right.
Yeah.
So PowerPoint.
1
Okay. So this is what I did. I said we have to do experiments. We are at CFA doing science, but this is science, right? So I said we have to do experiments with humans. And I met this fellow. His name is Matthew Schneps, who mentored me at the Center for Astrophysics. And he had been able to prove that people with dyslexia are more sensitive to small events happening at the periphery of the visual field when they are analyzing astrophysics data than traditional astrophysicists. But traditional astrophysicists, they are only sensitive to events in the center of the visual field. He tested this, he proved it. So we came up with the notion to simulate the task astronomers use to work on the detection of black holes. It comes from the idea that there's a black hole in the center of the galaxies, and what the astronomers working on this data, what they do is that they do hunches, because sometimes the discovery surveys, they have from 10 to 1,000 of candidate galaxies. So their decisions sometimes are go, no go, go, no go, because sometimes we have to save telescope time. There is a factor that we have to take into consideration highly. Also, sometimes the data analysis packages are limited. We're limited by different states in our data analysis, mathematical states in our data analysis. And we simulated the data, we took people that had already done at least 2 postdocs, that had a number of publications in their field, so they had the same level of expertise doing this kind of data analysis. And we had them identifying, we simulated the data, you may be seeing the characteristic spectra or plot for when they're trying to identify. You're seeing the characteristic spectra of which is a spectra that has two symmetric lumps. Do you see it?
Mhm.
Yes, 2 symmetric lumps. And what I did is that I either decreased the signal or deprived them from sensory modalities. They were either blinded to the signal or they were either hard of hearing to the signal. See? But I didn't block their ears or cover their eyes, right? What I did is that I removed it from the screen. So we exposed them to different parameters, different combinations, sound only, visual only, sound and visual together, and those things. And it happened that we found that their sensitivity to being able to identify those signals at different angles of visual field increased greatly when they were using the 2 modalities. And to us, that was really remarkable, because sound has been around for how many years? Since the first one heard it, right? And it has taken so long to get to this point when it's beginning to become something that may help to identify things. For example, task of vigilance, when someone is vigilant in the airport, and perhaps using sound as an adjunct to visualization may help them to identify changes that may be or may endanger our security. See? So we were able to test that, and I know this presentation has been a little bit awkward. What's that slide?
What we found.
I already told you that. I already told you that. Thank you, Jim. Thank you. So this is the data that I'm working now with. I've been listening to it. You only have 65,000 data points of 2,144,000 data points that I've been listening for the last 4 months. Yes, December, yes, for the last 4 months. This project is called LIDA. Have you ever heard of LIDA?
No.
It's the large aperture. LIDA, it doesn't make sense. Large aperture experiment to detect the dark ages. We call it LIDA. That's the acronym for all that. LIDA, what it wants to do is an array of radiotelescopes or interferometers or interferometer. That what they want to do is to be able to detect the hydrogen line that is characteristic of the universe when the universe was about 300 million years old. Quite young, about 1% of the age it has right now, right? So my task right now is to be able to isolate those frequencies from that data. So what I'm doing now is decomposing the data into its different oscillation modes. It has taken me time. I will play the time series for you because I want to have the engagement of coming back and report results. And because I know that the PI is waiting for the result, he'll see the streaming. I told him I will play the data for you. So we will have to go home, work really hard on the data and produce results to present you that later. This data is not available. If you seek for LIDA data, it's not available yet. You will have to wait a little longer to, but it will become public because it's sponsored by the National Science Foundation, and all this data goes public. So I'm going to play. As I said, it's only time series. Do you see that coffee cup?
Yes, to the right. There you go.
And we need to press play.
It's down in the bottom of the center. Trying to use the mouse upside down.
Okay. It's too fast to make sense of it, right? It may look really noisy, full of interference. Regularly, you will get rid of that. But there's ionospheric effects. There's also frequencies that you're very interested into. And I hope to be able to report good results very soon. If you have any questions,
So do we have questions? And Kevin's going to bring a mic to the questioner. So in the back here, should we turn that off?
yes.
So thank you very much, and we can take questions.
Thank you very much. This one.
Yes.
Thank you very much. That was just so fascinating. I just want to know, how do you know which sounds are actually giving you data?
Yes.
And which sounds are just noise?
Periodicities.
Periodicity.
I try to identify first patterns in the data. And then I go to the local conditions of anything that I'm listening to. For example, if radio astronomy data, then I go to the local, how is the ionosphere behaving at that moment? Or how were the devices in the monitoring the radio telescope or managing the radio telescope behaving? Satellite data, the same thing. I go to the local conditions and then I know if it is and this is long before applying any mathematical analysis to make things more salient. Yes.
Thank you. Is there another question? Yes, the woman in the middle here.
Do you create a control?
A
In
control.
other words, do you take a specific kind of data and you make a particular tone for it,
Mm.
and then when other data comes in, you recognize that as the tone you made for that piece of data?
Always the first, when I take a long data set, I listen to like 500 data points first. That is my baseline. The second piece of data of the same data set that I take will overlap the first data set for perhaps 10 minutes or 5 minutes. 5 minutes in the time series, right? Not in the audio realm. It will overlap. So then I carry working memory with me. So I'm able to identify, yes.
So Wanda, can I
Thank you, good question. Thank you.
can I just ask a clarification of that?
Yes.
So if you are listening to data from a satellite that's crossing a magnetic field, does the intensity of that magnetic field, does that have a particular sound that would be the same if a different spacecraft were crossing a magnetic field of the same
It
intensity?
will be different. Yes, the devices are different.
The devices are different, so each device has a uniqueness to it.
Yes.
Yeah.
Yes, it does. It completely does.
Got here in the orange.
I call it has a different voice.
Each instrument has its own voice.
Yes, that's how I call it.
Sorry, my question is more to do with what is the new knowledge you have contributed to the field, which is
From the audification point of view.
yes, contributed something new that people will use the visual. Can contribute something new to the whole field.
Of sonification. Yes.
You publish
Yes.
articles and journals related to your findings.
I have submitted, let me tell you, I have submitted articles to Kai, and of course they haven't been accepted because of grammar mistakes. So that's what they write, right? They have so many grammar mistakes, it doesn't look professional. Well, but at least it's out there, right? But in astronomical journals, etc., yes, I have reported what we have found. For example, in the research that is open now, Intel and NSF are opening research on increasing human powers. See, in that context, then we are doing a contribution because we are increasing the sensitivity, your sensitivity to detect events, not only when you're looking at the chart, but this may be extrapolated to people when they're walking on the streets. And what I said before, when they're carrying out vigilance tasks, which is a priority of governments and even schools, etc. But other applications, as I was mentioning last night, which really has my heart, I really have the heart on this one, is on helping people with Asperger's if they want to, right? Helping people with Asperger's and helping people with autism to develop prosody so they can identify social clues like irony, laughter, shame. I really have this one on. I mean, I love my science, and I love to be paid to listen to these charts and sit on that desk the whole day just listening to this. But this is something that I see a big contribution that can help a lot. Yes. Yes.
Awesome. Have we got another question? We've got about 10 minutes. I saw a hand in the back.
And we have gifts.
Yeah. Kevin's been giving everybody a solar lenticular for asking questions. Yes.
Well, thank you, Wanda, for that beautiful presentation. It's a very big eye-opener. I want to know this. In radio astronomy, sometimes you make observations, the data you have got bad data and good data, the spectrum, and you have to kind of reduce data to get a good one from bad ones.
Yes.
How can you identify that the data you are using is a bad data and is a good one from your system?
Again, in my case, it's because of periodicities. If it is too periodic, it's man-made. I have no doubt it's man-made. If it is quasi-periodic, then that really elicits for Wanda to do a little bit more research on those periods. But what I listen for is for patterns in the data. When am I listening to this, and how many times am I listening to this? See, because even radio data is noisy. It carries a lot of things that are, I don't want to say garbage, but unuseful, perhaps. Yes, let's call it unuseful, not to say garbage. You have to delete that from the stream. Yes.
Okay.
Thank you. And that is my approach to the data. Also, I keep in mind, for example, mathematical. This is an amplitude, or this is a frequency intensity. So I keep that in mind when I'm listening. I know what is being drawn in my mind mathematically when I'm listening to the data.
So we got another question. Yes, in the middle here about Can you hang on 1 second? We'll get you your mic.
We have to develop training for people to use it and for it not to be time consuming.
Thank you, Laura. I was interested, have you done any work on the solar system? Our sun is pretty noisy, Jupiter's noisy. I mean, have you been interested in the solar system at all? And the noises and the sounds coming from it?
Well, when I did the crossing data from, it was crossing data, it means going from one planet to the other, right? Without having any magnetospheric or any planet effects on the data. Is that correct? Because there will always be an effect, right?
Yeah.
But not formally getting in there. See, so the mathematics will, you know what I mean, right? Yes. So I've been doing work. If you mean the space within the planets,
yes.
With planets in itself, we've been trying to work on Kepler data and listen to the photometric points and the length of the nodes to give us ideas of typical transits. But that is a little bit distant because I have the data and I haven't heard it. Yes.
when I say our sun is very noisy, I thought.
Yeah. And it's very complicated. So.
Thank you very much.
Yeah. Thank you.
Are there more questions? Yes, this young lady over here on the end.
I just wanted to ask, if stars and planets and comets are all giving sounds, how do you tell the difference between whether you're listening to a star or a planet?
They don't give sound.
Are they giving certain lights? And you're
Well,
converting
yes.
sound?
Yes. Because it's light, what we get, right?
So are the planets reflecting the light of the stars, and that's being turned into a frequency by the
Yes,
program?
I convert it into sound. And I listen to it.
So then the planets have different frequency than the stars?
It depends what device you use to, because you can measure planetary emissions from Jupiter using different frequencies like 21 megahertz. What other frequencies can we use for planetary emissions from Jupiter?
Oh my goodness, I really don't.
There's you get, it depends on what device and how it is centered, right? The data from LIDA is 21 centimeters or 1.4 gigahertz because we're looking for this hydrogen line. This one in hydrogen that is particular to this. But I can center my receiver to other frequencies in order to detect other things, variations in other particles, perhaps in the magnetosphere or different points. It depends what frequencies you want.
So, you use the analogy that every sensor has its own voice.
Yes.
You could also use the same analogy that when we fly a spacecraft to a planet like to Mars, or to Venus, or to Mercury, we put as many instruments on board as we possibly can. Imagers, magnetic field sensors, particle sensors, radio frequency experiments. And what I believe you're saying, Wanda, is you're willing to listen to all of them,
Yes.
right? So they're like different instruments in an orchestra. Each has its own unique sound.
And you know the device. You know the device, you know what the device is gathering, how fast the data is being gathered. So how fast is the sampling frequency? The time, the inverse of time will give you a frequency as well. So all of that you know when you're listening to the data. So you can identify exactly what it is. Thank you.
So we have about 5 more minutes before we have to break. Are there more questions? I have a couple for the chair. Yes, the gentleman here in the quick side.
It must be a beautiful sound that you attach to the background radiation, the 3 Kelvin. Do you listen? Well, I mean, you have to take that away, I suppose. It must be a beautiful sound. The background radiation, the 3 Kelvin background radiation, that's residue from the Big Bang.
We hope so.
Yeah, and the sound. What have you attached? Well, you would attach something to that. What would it be? Very low growling noise or?
If I would attach a meaning, because that's what you're doing.
Yes.
Assigning meaning to this data. A question that may be answered with these LIDA data that you heard just a little bit of it, is the first stars. Were they the same stars? Were they the same sources as the stars as we have in the skies nowadays? Evolution of massive black holes is another possible meaning. Possible. I said possible. Remember, the PI has to sit down and has to listen to this. It has to see my analysis. It has to, right? I'm not saying this is it. Yes, that's clear. But for example, the evolution of black holes, where massive black holes progressively became to like this, or were they like this when the universe was so young? Also, information on the transition from when the universe was mostly dominated by magnetic gravitational influences to when it is now more not so dominated by gravitational. See, all of that information we can get it from
I'm not assigning that meaning to this data now. I'm not saying that that's what we found. Yes, next year when we come, we tell you.
So, and we had a question here in the middle, two down.
Thank you for that question.
I was just considering in the situation where logistics around would use your technology to process all this data, all this massive amounts of data, so that the SK will what to process, like logistics around with listening to all this streaming data.
I don't understand the
That's
question.
not really a question. Just trying to formulate a proper question. It's just it's very useful. I can see the application here.
Yes.
So he's pondering the fact that SKA is going to generate an enormous amount
Oh, yes.
of radio
Yes.
astronomy
A
data.
person, a really talented person, that can actually just use this technology to listen to the frequencies and sounds,
Yes.
to do all that processing for you instead of a super computer.
Yes, yes. But more beyond that is the point that we can bring other perspectives to the field in order to enrich the perspectives that already are working on the field. Because it's a little bit out of fashion that technology has evolved so much, and I'm not complaining, but I'm going to open up my heart here with you. Technology has evolved so much, and we're still using over and over and over and over and over and over again the same approaches to data analysis. I think that if data streams are so huge, we need to bring other perspectives to the data analysis in order to do a better exploration, which will also bring other people to perform science at the level of Jim.
At the level of Jim. Dangerous. So that needs to be our last question, Wanda, but I'd like to wrap up just really quickly before we thank you and say anytime we have a problem and we apply diversity to it, we always get a new perspective and always seem to find new solutions to those problems. And I think that's one of the things that your research is bringing to us. You've mentioned the hydrogen line a couple of times. The hydrogen line, and you correct me if I get this wrong, but the way I understand it is that was an emission from one of the very earliest periods in the formation of the universe. And over time, because of the expansion of the universe, it has now redshifted down into the UHF, which is a very noisy region of the spectrum, the radio spectrum. But there are lots of scientists trying to chase radio spectra looking for this hydrogen line. And it's believed that the one that finds it may be up for a Nobel Prize. So sorting through all of that data, could be Wanda, sorting through all that data by listening to it instead of looking at the data may actually be a solution to trying to find this hydrogen line that's buried in the noise of the UHF spectrum. And so we wish you good luck with that. And thank you for your contributions. One of the things.
Thank you so. Thank you.
Hang on one second. You can't see it, Wanda, but we've got a gift for you from Scifest here, and the gift bag happens to match your shirt.
Oh, look at that!
There you go.
I knew it.
Thank you so much for coming.
You were really great. Thank you so much. To me, it's the highest honor to be here with you. I was a little bit nervous at the beginning, but the most important thing is to say thank you. I'm really thankful that you took the time to come and support the presentation. Thank you very much.
Thank you all.